Hey everybody, this is Bharat Muthuswamy.
And Amir Mokhtaderi.
This final lab lecture is on the course project Building an EEG or electroencephalogram or brainwaves interface.
Since this is the final project, we will combine ideas from all the previous labs and all the course material. So let's get started.
Okay, in this lab or project, we will work on the specified design problem. Since this is a design problem, there are many possible solutions. We will present one possible solution. Note that this work was accepted for publication at the 2012 IEEE International Symposium on Circuits and Systems, or ISCUS, which took place in Korea, May 2012.
Awesome, let's get started.
Yes, but caution. Since we are interfacing this circuit to a biological signal, there are safety issues involved. You must not try the circuit on yourself. Okay, we'll design the circuit by simplifying the problem into different subsystems. We first need to understand that EEG signals are on the order of tens of microvolts at around 10 to 13 hertz, at least the signals we're interested in looking at. Hence, there are three main subsystems. The instrumentation amplifier for high gain but low CMRR or common mode rejection ratio. Recall your instrumentation amplifier lab. Next, we'll add further filtering to the design. Specifically, we need to filter out 60 Hz or 50 Hz if you're in Europe, for example, 60 Hz or 50 Hz noise.
We will need an isolation circuitry for safety and also a standalone power supply. Finally, we will use a digital backend for post-processing EEG data. This LabVIEW program will be provided to you and is courtesy of Winthrop Williams. Now let's look at the overall circuit and then work through each system individually. In the schematic shown, U1 is the instrumentation amplifier. C1R1 is the electrode DC blocker. U2A is another gain stage with high frequency filtering. The reference for this circuit is usually connected to the subject's right ankle and is also called as the driven right leg, or DRL. U2B and U3A function as gyrators or impedance inverters. These op-amps implement 25.7 Henrys inductor at 60 Hz. Note that we can choose different component values for 50 Hz line noise. We will discuss isolation circuitry and power supply separately, and they are not shown here to avoid clutter.
Okay, let us start by working with the instrumentation amplifier.
In our circuit, we have used the INA114. The gain is approximately 100 with a common mode rejection ratio of 100 decibels. Note that in lab, you will build an instrumentation amplifier from the standard 3 op-amp setup. Next, we have the DC blocker to remove DC noise from the electrode, followed by a 100x gain stage. Note that our EEG signals have now been amplified by a factor of 10,000. We also have C2 for filtering out high-frequency noise.
The gyrator is used to implement the 60 Hz notch filter. From the impedance expression, you can see that the gyrator is an impedance inverter. In other words, you have a small parasitic resistance RL in series with an inductance of value RL RG CG. So the gyrator implements a 25.7 Henry inductor at 60 Hz. Attenuation of the notch filter was 46 dB at 60 Hz. Hence, cascaded notch filters gave an attenuation of 92 dB at 60 Hz. The INA114 CMRR, or your instrumentation amplifier CMRR, took care of the rest of the attenuation.
For isolation, the ISO 122 is used. Plus and minus VS1 powered by batteries, and plus and minus VS2 are powered by the external power supply, which also powers measurement instruments, and etc. Isolation is provided by galvanic capacitance between V out and V in. In lab, you may use a different kind of isolation, such as an opto-isolator.
Okay, as far as the power supplies are concerned, the circuit is powered by external plus or minus 9 volt batteries. We simply used two voltage regulators to obtain plus or minus 5 volt power supplies for the amplifiers and filters.
Here's a screenshot of the LabVIEW program. Now let us show the circuit in action via the demo.
Okay, now for the project demo. Again, please do not try this project on yourself. Note that we'll be showing EOG signals. For EEG signals that we published, we obtained the data from the occipital lobe at the base of the skull once rubbing alcohol has been applied. We use rubbing alcohol because we have surface electrodes, so we needed to clean out the dead skin. Okay, so what we are showing you here are the printed circuit boards which are actually built by the students. This is not a student-built printed circuit board. This is the isolation board over here, and this here is the board which has the instrumentation amplifier, the DC blocker, the gain stage. Now, if Amir, if you show this little box here, this was a box which was built by Winthrop Williams. This has the isolation circuitry inside, and this connects to a populated student board over here, which is powered by batteries, and the output from the from the student board goes to the MIDAC, which now goes to the computer which is running LabView. So if you want to show the screen here, so here we have some data, but now what we're going to do is we're going to do a kind of like a live demo of the electrodes connected to Bart's head, and Jared Porter at EE40 Summer 2012 TA has volunteered to help us shoot the video. Okay, Amir is recording, and you can see the time waveform over here all over the place. What it's actually showing is electromyogram activity as I'm talking. So you're going to see some silence for some time because it's going to let me get a baseline, and then I'm going to blink. So when you see spikes, that's me blinking, and Amir will call it out. So I'm going to shut up now for 5 seconds, and then we're going to start.
There's a blink.
Actually,
There's another one.
Oh, yeah.
Yep. There's another one. And another one.
Yeah, exactly. So all this is doing is it's reading the EOG, but the point is you can see how much noise there is in the data. So it's me blinking. Well, the blink's pretty good. It's like 1, 2, 3, 4, 5, 6 blinks. But yeah, so if you want to get EEG, you should not do it. For the ISCAS paper, we got it from the base of the occipital lobe. But do not try this on yourself.